We present our work named NODEO, a neural ordinary differential equation-based optimization framework for deformable image retrieval. Deformable image retrieval, aiming to find spatial correspondence between images, is one of the most critical problems in the domain of medical image analysis. Given the fixed image I and the moving image J, which are functions that map the voxel coordinates to intensity, the goal of deformable image retrieval is to find some good transformations such that the warped moving image J is similar to the fixed image I with desired constraints on the solution transformation. Deformable image retrieval is traditionally formulated as pairwise optimization problem. The optimization objective is the combination of similarity metric S and the regularization of the transformation R. In this paper, we follow the pairwise optimization manner. For any given two images, our framework conducts retrieval by optimization without learning from data. In this paper, we model each voxel in a 3D image as a moving particle and consider the set of all voxels as a high-dimensional dynamical system whose trajectory determines the target deformation fields. In our formulation here, consider a 3D image. The location of all voxels can be denoted by an ordered set, or we call voxel cloud, Q. Q0 is the initial voxel cloud, when none of the voxels in the cloud has undergone transformation. We use neural network to identify and solve the dynamical system, which represents the evolution of flow fields that continuously deform the space, which we will elaborate later. We start our method from general neural ODE. Neural ODE is a family of neural networks which minimize the following loss by updating the parameters of vector field F. Our work borrows intuition from dynamical systems and treats the trajectory of the entire voxel cloud as the solution to an ordinary differential equation, shown on the left. While V theta, parameterized by the network, is the vector field describing the dynamics of the voxel cloud Q. Q0 is the initial condition at t equal to 0. We employ a Gaussian kernel at the end of the network, denoted by K as a filtering operator to enforce spatial smoothness in the domain of image. For each time step, the input of the network is the current coordinates of voxel cloud, and the output is the velocity field. A voxel cloud first gets downsampled using convolution layers. It then passes through dense layers and gets upsampled back to the shape of the input voxel cloud. The trajectory of Q is generated by integrating the ODE in the equation above. With the initial condition Q0, the resulting final transformation is given by the equation on the right. After we get transformation, we can warp the moving image and calculate the similarity loss between I and warped J. The similarity here can be mean squared error, normalized cross correlation, mutual information, and so on. The optimization objective is shown on the top. For image retrieval, there is usually no ground truth for optimal solution. The solution transformation family is a choice one makes based on the application of features one seeks to develop. Starting from generalized flow field approach and then specializing to image retrieval, our framework makes embedding proper dynamical constraints straightforward, allowing flexibility in terms of defining task-specific coordinates for our transformations, and producing solutions with desired regularization. For example, we use negative Jacobian loss to ensure the transformation is diffeomorphic, and we regularize the transformation to be energy minimized and smooth. We also show our framework can add temporal assumption on the system. For example, here the intermediate images act as constraints along the transformations. We unify the optimization problem of discovering differential equations and their solution in one network. This figure showing the experiment discovering transformation on multiple images. The target image I, J, K are shown in the top row, and the task is to identify a path of transformation from I to K via J. The pictured registration results are from using a time-varying system with explicit time embedding, and B, a time-invariant system where the transformation does not depend on time. For more details, please refer to our paper. In the following, we show visualization demo of our work.